certain situations you can kind of theoretically figure out how much energy should a particular process be using. So like here we have a solvent distillation plant, and so their job was to take dirty solvent and clean it up. So they have a bunch of distillation columns. I think they had about 6 or something like that. And so based on the specifications of that different equipment, we can do some energy calculations and figure out that with this total steam consumption, 1,000 pounds per hour, theoretically that translates into 41 million BTUs per day. And what they were actually using was 300 million BTUs per day. You know, so the recommendation was, well, there's a big gap. You have lots of leaks, and we expect you to be using, you know, more than $500,000 less steam than you are currently. I think you ought to have a look at that. So here's another facility, Crankshaft Manufacturing facility in Danville. So they have an induction heating process. So they receive these great big cylindrical metal hunks, and they put it in an induction furnace. So it's an electric furnace. It's not resistance, but it's on the principle of induction heating. So you have, if you subject metal to an alternating current, that will induce heating. So I had an opportunity to visit this place, and we did some disaggregation of the energy use there. The processes associated with heating up that metal, conditioning the electricity to, you know, for those induction furnaces was a big chunk. And so this facility specifically wanted to dig deeper into that. So this is kind of like a process of chasing the energy flows. So we have in induction heating, we've got electricity input, and then you have these power converters. Sometimes they're called transformers, lots of different names for them, but they change the electricity into something that the induction furnace wants. I think they had like 12 stages, so it was like induction furnace, break, induction furnace, like 12 times. And so they're interested in looking at, well, what are some energy efficiency opportunities with this? And so this represents the thickness of the arrow represents the relative proportion of energy going in. So we have the electricity input, some of that's bleeding off for cooling pumps and cooling towers. So in the induction furnace, you're trying to heat up metal, but then you have these copper conductors that are bringing electricity in. Well, you have to cool those things off, otherwise they're going to melt. And so there's constant cooling water going through these copper conductors. And then the other thing is you've got this thing called a skid rail. And so it's a stainless steel pipe, and it's just the thing, you've got these metal billets and they slide across the skid rail. Well, stainless steel in those temperatures is going to melt and deform and, you know, lose its mechanical properties. So they're constantly cooling that thing too. So we have a known electric input, and then we have known flows of water and known temperatures of water. So if I have a heat exchanger where I know the flow rate of water and I know the temperature on one side of the heat exchanger and the temp on the other side, then I can figure out how much energy went into there. And so I was trying to steer them in the direction of, well, you know, maybe this is an area for research, looking at some alternative materials, say of the skid rail. And so one of the other things that this kind of diagram does is it shows how a change in one part of the system changes, it kind of cascades through the system. So if I reduce the energy loss here, that means I need less energy here. If I need less energy here, it means I need less here, and I have less conversion losses. And so you can see this cascade of, you know, you change something in one place, and that has impacts upstream and downstream.